Alright, hi everyone, you're welcome to my YouTube channel, City of Electrons. And in this video, we are going to work an example on single phase. Okay, single phase line. So just do well to watch the previous videos because we are going to make use of formulas and ideas we've established in the previous video. We are going to apply them as we work different examples. So now a single phase, so this is the example here. A single phase load of 200 kVA is delivered at 2500 volts over a transmission line having resistance 1.4 ohms, reactance 0.8 ohms. Calculate the current, voltage and power factor at the sending end when the power factor of the load is A, unity, that's one, B, 0.8 lagging, C, 0.8 leading. So the first thing, very simple approach, is just to collect data collection. So the power at the receiving end, we've been told, or we've seen, that is 200 kVA, which is 200 times 10 to the power of 3 VA. Then voltage at receiving end, that is delivered 2500. Then the resistance, of course, R 1.4, reactance 0.8. So those are the given data. Now we have to calculate current. We have to calculate current at sending end. Okay, that's IS. Then VS, voltage at sending end, and also power factor at sending end. First case, when power factor is unity. Recall that we've said in previous video that power factor is cos phi R. So the power factor at the receiving end now is unity, meaning cos phi R equals 1. So all we have to do, just make this guy phi R subject formula, and then take the cos inverse of 1, and of course that's 0. Okay, cos inverse of 1 is 0, meaning phi R equals 0. Okay, so now that we've gotten that value, just keep it somewhere, okay, like it's written here, because we are going to make use of it when determining the current. So this is the phase at the receiving end. Okay, phase angle 0. So recall that for a single line, a single phase, VS equals VR plus the impedance, line impedance, multiplied by current at the receiving end. So then what we have to do, since we are looking for voltage at receiving end, at sending end, what we have to do, this value, you plug it in. We already have this value. VR is right here. Okay, here VR, we have VR, but we do not have this, and we do not have this. Recall that this equals your reactance plus the resistance. Okay, so we just substitute in the values like this. This is 1.4 from what we have here, 1.4, and for the reactance is 0.8. So we just put in those values, 1.4 and 0.8. Okay, and then to represent the impedance in polar form, we need its magnitude and its angle. And to get the magnitude, we take this square of this, and then the square root. That's the magnitude. We've done this formula in the previous videos, and then we just plug in the values or substitute in the values, and then we'll get this as the answer. Please punch your calculator and be sure what we've done here is correct. And for the angle is tan inverse of the reactance divided by the resistance, and of course the same values, and when you do that you get the angle for the impedance. Okay, note that the reactance here is positive, the resistance is also positive, so in that case that means the angle is in the first quadrant. That is, when you have this, okay, you have this guy is for this reactance, and then a negative reactance. So when both of them are positive, this guy is positive now, so that means it's somewhere here, okay, like this area. This guy is also positive, this area. Then this guy, so this is positive, okay, so it's in this area, like above. Negative is below is negative. Then for this guy is also positive. Look at it, it's also positive, so that means it's at this side, okay. So where they meet is at this part. This is where they meet. That means the angle is at this first quadrant where both of them are positive. And from that idea of 4 quadrants, for the first quadrant, this is the first quadrant, this is the second quadrant, third quadrant, and the fourth quadrant. That idea of quadrants, for the first quadrant, theta remains theta, okay. So thank God that in the first quadrant we'll just leave it like that. Now in case this thing I just explained here, it looks somehow, don't bother much about it, okay. All you have to bear in mind is that you just do this, carry out this operation, and you get your angle. I was just trying to put additional knowledge here, which kind of not really relevant at the moment, okay. So let's continue. So with that, we've gotten Z, we've gotten the magnitude, and we've gotten the angle, okay. Then for IR, this formula, power equals voltage multiplied by current. So therefore, if you take the voltage and you divide it by the power, you get your current, okay. And we already have power at the receiving end, we have voltage at receiving end. So that's what we did here. That's what we did here. Power at the receiving end, PR, look at it. Voltage at receiving end, look at it. So we just substitute in that value to get our current. Already the receiving end phase angle, it's 0. We've done that already, which is this. It's 0. So that's for your current. So since we now have current at receiving end, we now have impedance, and we also have this guy. We have this guy already right here. We also have this. All we have to do is to substitute into equation 1 to get Vs, okay. So substitute into equation 1. So we plug in all those values, we have this. So this is for the voltage at receiving end. This is the impedance. Look at it. This is the impedance. Z. Look at it. Impedance. Then for this is our receiving end current. So all we have to do at this point is just simplify. Okay. This will multiply everything here. Will multiply this. And when carrying out multiplication in polar form, you multiply the magnitude and then you add, multiply the magnitude, then you add the angle, okay. So this plus this will give you this. So and this magnitude 80 multiplied by this magnitude 1.6, it will give you this. And then when you add the angles 29.7264 plus 0, it will give you the same thing, okay. Then after doing that, since this guy, this point, let's go closer. Since this point like this is in polar form and this guy is not in polar form, what we have to do is to convert this guy back to rectangular form so that we can do the addition here. And to change this guy to rectangular form, it's just like what we did to the impedance, like the reverse. So what you have to do is this: take the cosine. Let me just write the formula out so that it'll be easy to get. Now that can be written as cosine of the magnitude, okay, plus J sine, okay, cos theta, please, or let me use phi as we've been doing since. And this magnitude, let me bring it outside so that it will be neat enough for us to see better this way. Phi, then the magnitude should be as I think it's neat this way. So I was thinking of just put the magnitude here, like multiply by this and also multiply by this, but it's better this way, neat. So take the cos of the angle, multiply by the magnitude, plus take the sine of the angle, multiply by the magnitude. That's what we did here. So cosine of this, that answer multiplied by the magnitude will result in this. Please punch your calculator and be sure. Leave comment in the comment section if that's correct. If this is correct. Then for the J part, the imaginary part, take the sine of the angle, multiply by the magnitude, and then you have this. Okay, now when that is done, we can see that this is the real part, this is also real, so we can sum these two, and that will give you this part. Now we have a real part and what? Imaginary part. Now to get back to our polar form, we then take then we do this then we do this, the magnitude and then the angle. Of course, this squared plus, let me see if I can write that somewhere. Okay, erase this part. So let me see if I can write that somewhere to make things easy. So we take this 2612.0171 squared plus the imaginary part 63.9618 squared, and then so if you do this, you get this number exact. That will give you the magnitude. Then for the direction, that's the angle, you do this, saying to the imaginary part, which is 63.9618 divided by 2612.0171. Okay, this, let's take out this guy. Yeah, so you take the tan inverse, of that. Okay, and this will result to 1.4 degrees. Okay, so with that you have successfully converted this from rectangular form to polar form. And of course the magnitude, this is the magnitude, that's the receiving end voltage. Okay, so by doing this, we've derived our sending end. This is also the sending end current. Why? Because in a single phase, the receiving end voltage equals the sending end current. We did that, of course, previous video, so please check that out. Okay, now for the power factor, which is cos phi s, this angle, this phase, is the difference between the phase angle of the voltage and current. So for at this point, since it's the difference, that means the phase angle of the voltage 1.4, which is this, minus the phase angle of the current, we got that to be 0. When you minus this, you get this. So you just bring in this thing 1.4, put it here, cos phi s. Phi s is 1.4, right? So cos 1.4, that will give you 0.9997 lagging. Okay, lagging, because we've already calculated this guy, or we're told. Okay, that's in the next question. But we know it's lagging. Why? We know it's lagging because the phase angle of the current is less than the phase angle of the voltage. Whenever the phase angle of the current is less than the phase angle of the voltage, we say it's what? Lagging. Okay, We also said this in the previous videos. Wow, a lot has been done in the previous videos. So that's why we have that as the answer. Okay, so in the next video we'll give analysis to that is analyze the answer to the B part. Okay, so just pause the video, go through this over and over again, and then let me know in the comment section what's up. And yeah, thanks a lot for watching. I'll see you in the next video, and bye for now.